warm welcome to the third day of our 6-day online ATAL FDP program. And I strongly believe that you are thoroughly enjoying the lectures of the sessions. And today also we have come with two exciting two renowned resource persons. Basically, you know that in today's era of new education policy based on outcome-based education, we have to imbibe the knowledge of implementing whatever we are learning from books into real world. The real world implementation of the technology or the engineering knowledge we are gaining over our BTech or master's curricula. I mean, it's playing a very significant and important role nowadays, specifically following the new education policy. So for successfully accomplishing this, we need two things to do. First of all, as faculty or senior researchers, we should have the proper knowledge of how to implement the real world scenario. And then, of course, imbibing the similar knowledge to our juniors and our students. And for that, we are having the industry persona to present their work experience in this FDP. And today we are having two such eminent people among us. So first of all, we are having Dr. Arup Kumar Sadhu from TCS Innovation Lab. Just as a formal introduction to him, Dr. Sadhu received his bachelor's degree from Asansol Engineering College under West Bengal University of Technology and his master's from Jadavpur University. He received his PhD engineering degree in multi-robot coordination by reinforcement learning from Jadavpur University in 2017. Currently, he is working with Tata Consultancy Services Research as a scientist. His research interests include, but are not limited to, reinforcement learning, game theory, mechanism design, artificial intelligence, path planning for robots, task scheduling for robots, and task and motion planning. His PhD thesis is jointly accepted and published by IEEE and Wiley as a book entitled Multi-Agent Coordination, a Reinforcement Learning Approach. So with this, I know that this introduction falls short for Arupda because he is really a brilliant person, and in our lab we used to refer him as the robot person, robot man. So I believe today also he is going to have an exciting topic with which you will be significantly enlightened. So it's all over to you, Arupda. Please continue with your presentation.
Yeah, thank you, Dr. Pratyusha, for such a wonderful introduction. So let me share my screen and to know whether it is visible or not. First of all, am I audible? Clear?
Yes, you are.
Okay. The screen is visible, hope. I hope my screen is visible.
Yes, visible.
Okay. So good evening, everyone. So today I'm here to present one interesting topic, that is simultaneously learning as well as planning within sensing range. That is mostly for a local path planning approach. Now let's spend some time on this title itself, then I'll go in details. So mostly people do learning. That means so many learning algorithms are available. Everyone knows so many top algorithms are for learning, from AI, machine learning, reinforcement learning, support vector machine learning algorithms. So many things are there. so many deep learning algorithms are there, but most problem for the learning algorithms are they need to train in offline, and they need lots of data a priori before training. So they need a priori training in offline. And on the other hand, for planning algorithm, suppose a robot needs to plan from point A to point B, then it needs to plan while it's in the online fashion. Whenever it's moving, it needs to plan. Or sometimes it's do planning in offline also, but it's possible to do planning in online also. Now, that's why we are main focus is to why can't we do simultaneously learn as well as plan in real time? Because we human being, whenever we do some task, we not only learn always, and learning means I have the person is going for some different trainings of this so many things, and after completion of the training, it's doing some job specified job. But sometimes we also in real life, while we are doing some work, also we are gaining some new experience and learning from it. That's why we human being always do that is called simultaneously learning and planning. The same thing or same concept is trying to import in the field of robotics is done this work. Now, why I have called it within sensing range? Because robot sensor have some limitation. It's do these all these things in its limited zone. That means within sensing zone. That's why it's called local path planning. We have another work previous prior to that work that is for global path planning. That is the main. That is the beginning of our simultaneous learning and planning. That reference I'll share later. So, before going in details of this work, I want to a brief introduction of some prior works that is called reinforcement learning. So, while we do reinforcement learning, let's see is happening for human being. So, whenever we human being do some task, maybe execute something, so for each action, it receives some penalty or some reward. So whenever a baby touches some fire, it's experience some pain, and because of that pain, its memory always reinforced with that the something with bright yellow colored something. It's giving pain to me, so it will never go to touch that thing. So that's reinforced for a human being also. The same thing can be happen for a machine like a car. See, if a driver faces some experience with particular combination of clutch, brake, and acceleration, then it will never do same thing. It will not never repeat same things in future. That reinforced the person's memory also. And same thing we can include inside a machine also in some form. That is called state action. So many things are there in reinforcement learning, but that can be done. The basic idea is that some penalty or reward in terms of some numerical value, so for a particular situation, and for a particular situation because of some action, that is some execution. So these things we do in real life also, even machine also do the same thing. Now, consider a single agent reinforcement learning. So, for example, in an environment, we can consider this is an environment. This environment has four states: one, two, three, four. Suppose robot uh, is currently at state 1. So if the robot goes from state 1 to state 3, then there because of some action A, maybe some left right movement, then it will go to step 3 because of right movement. So this is called one state transition, and that state transition is represented in this way, that because of action A at state 1, it will go to state 3, and that state 3 state transition is represented by in this way. So this is for single agent reinforcement learning. But that thing is all these things, whenever a robot do all these things in offline mode, in discrete fashion, we cannot instruct any robot that you go from a particular situation to a go to particular destination, maybe from one corner of home to another room's different corner. I cannot say, because robot don't know anything about the room, anything about other obstacles around it. It don't have any idea. So it cannot do all these things. It needs to be trained a priori. It should know what is the floor map of the environment, what are the other obstacles around it. It must know. Then only it can do this thing. Now, how this offline training can be done? This can be shown here. So one important learning algorithm in the literature is called Q learning. So this Q learning is basically update some numerical value in a particular fashion. So this update rule you can see here. This update rule is this. So the mechanism of this is that you can consider the same grid world I have shown here. The same grid world is here, and robot is at state 1, and it has 4 actions, that is left, forward, right, back. So it can go in any direction, and for each direction's movement from a particular state, robot will receive a particular numerical value. So if it's go to left direction, maybe hello, if it will go to right direction, then it will receive 0 reward. And if it will go and collide with the wall, maybe boundary wall, then it will receive negative value. And if it will move towards the goal action directly, then it has the highest reward, that we call immediate reward. So in the update rule we have two reward, one is immediate reward, another is future reward, that is discounted future reward. This and with this update rule, these rewards are continuously updated. Now how this future reward is updated? In futures reward, when robot will move at the next state, that is state 3, in state 3 robot will consider the highest value. In this case let us consider that state 3's values are already updated, okay, in the repeatedly by repeated iteration so many times. So it will consider the 100 mm, first time, and because of 100 gamma we can consider zero point 0.9, and it will update from 80.1 to 90 value. So in this way it will continuously update this value, and this process continues again and again. And this table we called it Q table. This is this side is state and this side is action. This is simple basic Q learning algorithm for offline planning. And for during planning, what to do? Suppose robot it as a state 3, and it will select the highest q value. This is called q value, and its corresponding action, that is forward. And if it will select forward, then it will reach the goal state. So in this way robot move at each state and move ahead. Now let's little bit introduce about the planning algorithm. So planning, this thing I have called about learning algorithm. So after learning so many things, so many iterations of them, I can do real time planning with these numerical values. Whenever this entire table is filled and saturated converged, then I can go for planning. But now I don't have that much of time for doing on this learning planning learning beforehand. And I want to plan in real time, then what to do? So for that I have divided planning algorithm in two parts. One is global path planning using gesture. So this is a basic global gesture algorithm. So basically there will be a heuristic designed for that, maybe based on mostly based on the distance from the start and goal, and some generation cost. So these are the basic heuristic algorithm. It will move from start to goal. I'm not going in details of the Ester algorithm because these are not main motto of the algorithm. And next is the dynamic window approach. This is called one of the local path planning algorithm. How robots works in this here? Suppose in a differential drive mobile robot, it will continuously generate linear and angular velocity to control the robot for a finite sample time, that is DLT. And you can consider that this global path is computed. Once the global path is computed, robot will try to attain this global path continuously, but in between it will receive some uncertain obstacle, dynamic obstacles, so many things, and it will avoid all these obstacles using this dynamic window approach, that is the local path planning. How it will avoid? It will continuously generate so many your this linear and angular velocity at the for different sampling time, and for each sample window it will continuously plan. Now this can be visible from this video. So here robot is moving continuously and facing so many dynamic obstacles, but its main motto is to move from here to there directly, but it is trying to avoid this global path. But here you can see there is a little deviation, but finally it will reach to its final destination, that is the main final goal. But while doing this thing, it is continuously trying to avoid so many dynamic obstacles when it is planning. So this is basically all these things are taken from open source. This is mainly implemented in robot operating system, this DW implementation, and these are available all these things in open source from Git and all these things. Now, now what how dynamic window approach, a little bit of idea because this will be necessary for the next slides. So DW basically generates some feasible linear and angular velocity following some conditions. So first it will prune the entire velocity ranges. Maybe velocity range has some maximum and minimum limit for each vehicle. So because and based on that limit, it will prune the entire velocity range, both linear and angular. And after that, based on some reachability criteria from the robot's current velocity, for example, you can consider that a car cannot move around its vertical axis, z axis. So it has to turn with some turn radius. So, that means a car cannot a car cannot move in with its all velocity. It has some feasibility limitation. So based on that, some criteria conditions, some velocities are discarded, and after that, finally, some collision-free velocity samples are collected, and how the velocity sample is collision-free is decided based on some safest distance from the nearest obstacle. So if there is a obstacle from the robot with some threshold, then that velocity is also discarded. Now finally it will select some optimal sample and from the final velocity set based on some score value. And this score value, this V is the linear velocity and omega is the angular velocity. And that score value is selected based on three conditions, three components. First is the angle, that means how mm, robot is directing towards its goal. And second component is the what is the velocity of the robot. And third component, that is the condition, the how far it is from the other obstacles. So it will try always push the robot from the nearest obstacle. And this is the dynamic window approach. This is the most famous work for local path planning. Now next, now how we this is the also requirement for understand the next phase of slides. So this one is the velocity obstacle. So this velocity obstacle basically lists all the velocities of the robots that leads to a collision with the dynamic obstacle. So previously, I have shown this video here. Dynamic obstacles are moving. So these dynamic obstacles are basically avoided using velocity obstacles, because in dynamic obstacle we have to estimate its future position, and this and that is done using this velocity obstacle velocity obstacle method. So how this is done? This velocity obstacle basically you can consider that there are two other robots or dynamic obstacle you can consider, and robot's position is here. So basically it will identify what is the velocity obstacle, and there are some some calculations behind this. You can refer this paper for these calculations how this is done. So the idea is that if robot chooses a velocity inside the velocity obstacle, then robots. Hello. Okay. Yeah, just a minute. Am I visible? So the main idea of this velocity obstacle is that robot must avoid this velocity obstacle, this velocity cone. This is called basically velocity cone. So there are two dynamic obstacle or velocities, VO1, this one VOB1 and VOB2. So this is the basically for multiple dynamic obstacles, we have to do the Minkowski sum, and any velocity within that Minkowski summed velocity angle must be avoided. And if robot choose any velocity outside that velocity cone, then robot is guaranteed to not collide. So this is the basic of dynamic obstacle avoidance. Now, what is the problem statement? So basically, our problem is to whatever the traditional algorithms do for robots. Uh, mm, Basically, they need lots of data to do calculations again and again. And for planning algorithm also, if the start and go destinations are near about same, then robot again need to do the same iteration for the planning algorithm also. So this is the main motto: is that the planning algorithm and learning algorithms combination. So this research proposed some new approach that is called local path planning that can learn as it goes, and instead of doing any offline training and repeatedly planning same thing. So this is the main motto. So we introduce a new framework that is called simultaneously learning and planning, and for within sensing range. And basically, this framework combines three things. This is the dynamic window approach, the velocity approach, velocity obstacle. Just explain this thing, and obviously the concept of reinforcement learning. Here we have introduced some new kind of learning algorithm, that is next best learning algorithm, to learn and plan a path at the same time. And we have done the convergence proof also of this, and time complexity analysis, so many things. And also one strategy is proposed, because if there is a learning algorithm, then there must be a question of balancing exploration and exploitation trade-off. So one strategy for the balancing exploration exploitation is also proposed. And and one important thing is that in most of the traditional learning algorithm, the number of state and actions are defined a priori, but here the number of state actions are dynamic. It can be generated on the fly while it is learning and planning. This is the mm, basic block diagram. So the block diagram for this one is that you can consider that there is a global planar A star. So this you can consider this global planar is A star. So A star is our input here is the floor plan where the robot will go. That floor plan, the entire map of the environment is given. Floor plan means not the exact map what is at current position. Floor plan means only the boundary walls, and only boundary walls, nothing else are given. And if any static obstacle that is fixed, that is given only. That is floor plan only. For example, in warehouse, the racks position, charging points, all these things are. This algorithm mainly developed for warehouse application. That's why I'm giving these applications examples. And the start and goal position, of course. So if the start and goal position is given and 2D floor plan is also given, then global planner, that star will generate one global path. Now using that global path, one local goal is generated. What is local goal? Local goal is required for local planning. So local planner must need because global path is very far away from its robot's current position. So one global path, one local goal, that means robot where to go immediately, that is required, and that is calculated using robot sensing range and the global paths intersection that I will show later. And with this local path is input to the DW algorithm. You can consider in both way, this way also, this way. Now here what is happening, as I told you just that each learning algorithm needs some balancing of exploration and exploitation. So the here my action, my actuator is the planning algorithm itself. So planner itself is an actuator. So what is my planner? Planner is the DWO. So initially when I don't have any path, when I don't know anything, then I am depending 100% on the planning algorithm. And gradually when I am planning again and again, I am learning from the planning algorithm, and gradually I am getting independent of the planning algorithm, that is with the help of next best reward learning. Now how this is happening? So whenever at the initially, if there is any path, no path, then explore using DWA. That means DWA with the local goal, with the local goal, dynamic window approach, that is do local planning and explore the new path, find out. and it's the input to my learning algorithm. And learning algorithm is learning and updating its reward table with specific state action. Now, what is state action? That is later thing that I'll come. Now, again, uh, after gradually when it is planning again and again and again, then it has some path that is exploitation. That means, oh, I have already planned for this type of, and it will get some exploitation. That means reusing the already planned information. Then it is taking information from the reward table and doing the exploitation of the DW. That means here DW dependency is reduced. And how the and while in the NBR, that is next best reward learning, here velocity obstacle is used for dynamic obstacle avoidance. And this entire highlighted blue grid area is the main contribution, and that is providing us the optimal velocity and execution. Now, next thing is that how the local goal is computed for DWA, and what are the state action reward in any learning algorithm mostly, but in total it is SLP, simultaneously learning and planning. Now, while doing local goal computation, consider this is a robot and it has a sensing range. Zeta is a sensing range, and this is maybe the start to goal position. Robot is current position here, and this is its goal position. So local goal, if the local goal, if the next waypoint, that means so basically global any global path, it's a collection of waypoints, XY points, nothing else. In 2D plan, currently in 2D fashion, we are dealing with 2D only. So it's a basically XY position. So if this XY position, that is P1, is within the robot sensing range, then that is itself it's a local goal. It has to attend the next waypoint first. But if it is beyond its sensing range, the waypoint is beyond sensing range, then we have to do the vector operation of this one, zeta into P2. So this is the local goal for our robot, and that is just on top of the sen sensing extreme range. Now, local computation. Now what is state in this case? So, state information, we have a few information that is before that I have to explain this one. Now, the entire sensing range basically divided by some regions that is called sector. So, this sector is nothing but the entire sensing range. This is the 360 degree sensing range. So entire sensing range is divided into a number of sectors. Sector means basically you can consider some angle, some section. Okay. So this is a one sector. This can be one sector. So uniform sector we have divided this one. That means where robot is facing some obstacle, all these things to identify those things. Simplify this thing. We did this thing. So state is basically a sector, a robot's velocity, linear and angular, and the QK. QK means the kth sector. So any obstacle in the kth sector, position and the velocity. So OK and VK. So this is the kth sector dynamic obstacles as well as dynamic obstacles velocity. So these things are my state. So basically, whenever driving a driver drives, so what it's look, its current position, where my car is, and I have my car's heading is which direction, and what are the dynamic as well as static obstacles around me, and what is my current speed. So based on that, a driver plans that in which direction I should rotate my steering as well as give what amount of acceleration. The same thing is there. Now, what is the action? Action is same, the linear and angular velocity in this case. Now, mm, what is the reward in this case? So for reward, what I did, mm, this is S and A, basically the state and action, basically state and action, the same thing. We'll refer now S and A for next way. Okay. Now for state action, this thing I have just explained before, this score value, this J of V omega, based on this score value, basically this score is high means robot is doing correct. Okay, it is moving towards its goal. If the score is value is low, then it's doing wrong thing. So based on that concept, we'll design the score thing, that is R max if the reward is high compared to current estimates. Okay, current system. This uh, A star means optimal action at the, so whatever it has experienced, whatever action it has experienced, that is linear and angular value at a particular situation, particular state. If that, if then, if the new, if some new action is experienced and that corresponding score value is high, then we have rewarded it. That means if something is new is experienced which is better, then we'll give highest score, highest reward for that action. And if it is low, then if it is low compared to anything which you have experienced uh, mm, previously, then we refer it as zero, immediate reward. These are called immediate reward. And if for any case, whether it is static obstacle and it is dynamic obstacle, we'll this case is basically dynamic obstacle. Question 5 I have taken it from paper. So I'll share the paper. I've already shared actually. So if it is not satisfied means the robot is not taking any velocity from the velocity cone. So it is taking some velocity from the x velocity cone. That's why it's not satisfied and it's a penalty. Now these are some mathematical details. I will not go in details about this thing. So all details. So what is next best learning rule basically? That's I simply explain and I'll go result section, make it more interesting. So NBR, how to compute the NBR value? Basically, in any reinforcement learning, basically there are two components I have shown. That one is immediate reward, another is future reward. So immediate reward is almost same. What is classically, basically we have new thing is the this future reward portion, this NBR. How this NBR is computed, and similarly we have introduced learning rate. With the learning rate, the same equation can be transformed in the same way. What classically we do. So this next best reward basically we compute. So basically we receive j hat, basically some action we execute, and based on the action, if some new action is better than the previous action, then we'll consider that highest reward. Otherwise, we'll avoid this thing, and we'll consider at the low rewarded action. So basically, these things. If something new is learned and new is better than the previous, then it's good. Otherwise, not good. So in this way, we have maximum updated the future reward. Now the same for that all these details you can refer this paper. This is published in IEEE Transaction in Artificial Intelligence. The paper, the work I am explaining. Now this some little bit analysis, the time complexity for to understand the essence of this work and complexity and convergence analysis little bit. So basically time complexity for this one is that consider that SLPSR, the proposed algorithm, that is at a particular state, if it is TLS, and time complexity for DWRL. DWRL we have considered as the contender algorithm because it's a learning algorithm, learning based planning algorithm. So that's why we have considered is the as the contender algorithm. So if we consider its time complexity as TRS, basically all details are in this paper, and time complexity for generating one optimal velocity sample by the DW, that is classical planning algorithm, then we can see that our proposed approach has less time complexity compared to this traditional approach, traditional planning algorithm, and it is very less compared to the learning based planning algorithm because it involves lots of training time, offline training time. Now for the convergence proof, we have proved that the proposed NBR algorithm converges at its state action pair uh, as time tends to infinity. The proof is included in the paper. Now simulation. So basically for simulation work, uh, what is happening? So this thing, the first simulation area, what we can see, a maze-like environment. Okay, here so many obstacles, vertical bars, static obstacles. These vertical bars are basically dynamic obstacles. They can move here and there. I'll show video. And these obstacles are static obstacles. And robot is here, and this is its sensing range. And if there is any obstacle, it is getting obstructed. And this is a zigzag-like environment. And this is the local cost map, or we can at present situation it is the local cost map for the world one. This we called it world one. And this one is the warehouse environment. In the warehouse environment, so many racks are there, so other people can also move. And these are vertical bar obstacles, they can move. And this is the corresponding local cost map of the world. And these are the current situation. These are the obstacle, and this is robot. And here this is robot, this is sensing range. And finally we have tested it for hardware experiment in our lab uh, with a simple uh, with a simple environment. This type of, because of the space constraint, we have did simple small environment. And this is corresponding cost map. And this we did using turtlebot 3. And so how, what are the setup? First I will explain what are the setups required for this doing all this simulation and experiment. So first of all, we did all this thing in Ubuntu 20.404 OLTS system. Ubuntu system we need Linux, and we have simulated this in ROS Noetic with Gazebo. ROS is the robot operating system, and its compatible version is Noetic with Gazebo. Gazebo, this is the basically Gazebo outcome. This is also Gazebo, and these are the RVs output, RVs screenshot, and these two are the Gazebo. Okay, in for Turtlebot. So in simulation, these two are done using Turtlebot 3 Waffle 5. Its version name, model name. And in simulation, in Turtlebot Waffle Pi is equipped with a 360-degree laser to perceive static and dynamic obstacles that I have shown here. These are the sensing range, and within sensing range, it is sensing whatever the obstacle, static or dynamic. And they are highlighted over here also. And the velocity range for the dynamic obstacle, we have considered plus minus 1 meter per second. Okay, in simulation. Currently, I am saying about simulation. And with with an inflation of 0.2 meter for why this inflation is required? Because for obstacle avoidance we need and safety also we need some inflation, but because whatever the obstacles dimension, we uh, we consider that obstacle is some bigger, sometime bigger, that is around 0.2 meter more the obstacle is. So for safety we have inflated the obstacle while doing the planning as well as learning. And velocity and acceleration ranges for robots are plus minus 0.2 meter per second and plus 0.27 meter, zero point 0.5 meter per second square. And for hardware experiments, we have created some ad hoc wireless network for real-time communication with the ground station, because all the computations are done in ground station in a separate laptop or desktop. And from that ground station, linear and angular velocity, computed linear angular velocity are sent to the robot, whatever computed or suggested by the algorithms. And the most important thing is the localization. For the localization, for hardware experiment, localization is very important, because in gazebo and simulation environment, we don't uh, we don't have to think about where robot is. We are continuously getting information about the robot's current pose, that is x, y, theta, roll, pitch, yaw, all these things we can get continuously from the simulation environment. But in real environment, we cannot fetch all this information continuously, because we don't know where robot is in my entire environment. So for that, we are using OptiTrack motion capture system. So basically, this is a motion capturing system. It is in our lab. So it is continuously give the, this is a laser, sorry, lamp laser. It's a IR camera with some marker placed on top of the robot, and we create some 3D object and with these markers, and continuously get that turtlebot's robot 3 information in our ground station. And for hardware experiment, the velocity range of the robot we have reduced to plus minus zero point 0.1 meter per second, and inflation is also increased for safety from 0.5 meter zero point 0.2 to 0.25 meter. And we have coded the entire algorithm in Python 3.11. Now, this simulation procedure. Now, how we did all these experiments and validate our algorithm. Uh, so first is the we have continuously observed linear and angular velocity of the robot and each iteration. Next is the average time. So average time we have computed with this formula, 1 by number of epoch. Here 1 epoch means robot reach from start to goal, one successful trial start to goal, or some particular after a certain iteration robot cannot reach the goal, fail because of some because of some obstacle, dynamic obstacle, some way it's failed, or then it's called one epoch. So for all epoch, we have gathered this thing and divided it with the number of epoch, and this is the runtime required to reach from start to goal. That is for one epoch. And next we have identified the what is the success rate. Success rate means whether robot reached the goal without collision divided by number of epoch. That is called success rate. Now another is the average path length. It's the average distance covered by the robot to reach the goal without colliding or randomly placed obstacle in all environment for across the successful trial already only. And next is the average velocity. That is the similar like average path length is the distance traveled divided by the robot took time to succeed without colliding any randomly placed obstacle. Now, this is the percentage of exploitation and average reward. These two metrics we have considered to validate our learning algorithm. That is the next best reward algorithm. This is also a proposed approach because based on that learning algorithm, the simultaneous learning and planning algorithm stands. So, for percentage of exploitation, we have just, as I told that in NBR, the number of states and actions are dynamic. So gradually, once it will explore, it will collect more number of states. It will accumulate more number of states. So that thing we have studied also. That is the ratio of number of states, exploitation number of states used for exploitation, and the total number of states at current states, and we make it percentage. And the average reward also, this average reward is also increasing with the as the learning algorithm converges, and we have just simply summed all the reward value across all the state action and divided it with the cardinality of state and action, number of state and number of action. And for hardware experiments, we are using Turtlebot Profile Pi, and for hardware experiment, we are basically creating one 2D floor map of the entire world for the experiment using the 3D LiDAR uh, disk map. Basically, I'm referring. We have created it a priori using 3D LiDAR in the placed on top of the robot. Now, some simulation results. Basically, uh, these are the three worlds. The world one is the zigzag one. Next to world two is the warehouse warehouse environment, and this world three the hardware experiments. So in these are the start and goal. The start and goal, and after some time we have tried with the random start goal, and these are the number of static and dynamic obstacles, and these are the epochs. So this epoch thing is very important. So initially you can you can see before going all these result details, you can try to see this essence that the epochs initially is 60. That means robots uh, tried so many times, robot tried so many times, so many iterations to reach from start to goal. Okay, because 60 epochs are, but gradually once it's gaining more experience, it is not taking that much epochs, it is gradually decreasing. So this is basically we have tested with DWA approach, dynamic window approach, dynamic window reinforcement learning. This one is that improved elastic band algorithm, potential field approach, this is preference-based potential approach. This is the traditional one. And one important thing in DWRL, runtime is used to average. This is included the offline training also for DWRL. The offline training time is also included. Now you can see that mostly in SLPSR the average runtime is low and variance is also low. And on this initially it is taking much time because it's dependent on the DWA, that is the planning algorithm, and gradually it's taking help from the planning algorithm and learning the best velocity samples. So, so this is the main thing. Now we have done the statistical analysis, and the p-value is very less than 5%. Therefore, we can conclude this table two's data are statistically significant. Now, these are the some results on success rate, average path length, and average velocity. So the success rate basically as satisfactory. You can consider in all world for these are the metrics: success rate, average path length, and average velocity. And these are the algorithms. And first we have tested it with static obstacles, then static as well as dynamic obstacles. So for all algorithms, success rate initially with static obstacles are good, but with the dynamic obstacle, the success rate for DWA and artificial potential field are reduced significantly. You can see here from 1 it is reducing, and this one artificial DWA. Why? Because they cannot handle dynamic obstacle. They are basically trapped in local minima. These are the problem of all these algorithms. But other algorithms are not too much poor. Specifically, DWRL is always succeeding. Now, average path length are also uh, is higher for other algorithm, but compared to SLPA, you can see here. And the average velocity for DWRL and SLPA-SR are almost similar and low for smooth velocity. That's so that robot should not feel any jerky motion. And next is the you can see here some simulation results of the velocities. So you can see this blue line, the SLPSR. These are compared to very smooth velocity line, the linear velocity, and this is the angular velocities. These are the two environment. This is for world one, that is zigzag environment, and this is in warehouse environment. So we are getting better velocity profile compared to DWA and other DWRL and all other algorithms. So this is in simulation. Now these are some real hardware experiments results with linear and angular velocities. Okay, so so we did it with ROS. We have recorded ROS time. Okay, so in ROS we have a clock. So that clock we have that clock's time, because whenever we started ROS, its counter its time continuously on. So once the robot sends the velocity, robot's execution starts. So for SLPSR, DWA and DWAR, we have considered for linear and angular velocities. So for linear velocity and in SLPA, SR is outperforming DWRL by this amount of seconds. But the most important, rather than outperforming, we can see here the velocities are smoother, continuous compared to DWRL and other DWA, both linear and angular velocities. Here you can see so many jerks here also, but this one is smooth. This one also linear and as well as angular. But here they can jerky motion, and here also smooth motion compared. So main idea is it's offering better velocity profile also while doing learning and planning simultaneously. So these are other sets of results for hardware experiments also. Here also you can see so many jerking motion here also for linear velocity, but linear velocity is smooth in SLPSR. Similarly, the dynamic angular velocity also smooth. Similarly, other experiments also jerky motion smooth for both for linear as well as angular. Now, this is the some results with NBR algorithm, that is our proposed learning algorithm for this SLPSR. So this is the percentage of exploitation. So it is gradually increasing with the epoch. So it is gaining or collecting more number of states. More number of states means it is covering the entire environment gradually as it is learning, and while its reward is also increasing. Average reward is also increasing. So this also confirms that its exploitation and exploration is balanced also. It is gradually exploring more number of states. It's not confined in a particular region. Now I'll show the accepted papers and published papers video. You can see here. So this is the same simulation. Now here, you can see the robot is. This is the static obstacle. The video is paused right now. So SLPSR is currently exploiting the learned reward table to learn the reward table to avoid the unknown obstacles. Okay. So here you can see the robot is where is the robot? Where is the obstacle? So it is continuously going from the same path. Okay. Start goal, different direction, different start goal. So this one is the gazebo environment. This one is the RVG output, and this is the just GUI. So robot is continuously doing or continuously moving from one state to another, one start to goal. So it is gathering information. So if it has some experienced information knowledge, then it is using that knowledge. Otherwise, it is just using the DWRL. Now this is the SLPSR. It's continuously moving, and while comparing with other environments. So currently these are the all static obstacles. In each environment, the static obstacles, they are moving. So you can see that this one, the proposed one, reach start to goal in a quicker fashion compared to others. So this one finished while other are still struggling. And this one is the zigzag with dynamic obstacle. So here you can see that vertical bars, these we can consider as pedestrians and other robots moving in each environment. So this one will finish faster. SLPSR will finish faster. Well, after reaching the destination, it is again coming back to its original position while avoiding the dynamic obstacle. As well as static. These are the static obstacles. So this one finished, and they are still struggling to reach their destination. Now I will show some simulation on warehouse after this one. So warehouse dynamic. Now in warehouse, so these are the, you can consider other peoples or other robots are moving while robots is trying to reach or picking some box, some order from one place to another place. This all the other robots are, other algorithms are also doing. The robots after doing some reaching there, it is again moving to its final destination from where it started. It is going again its original destination, start point. But still, these dynamic obstacles are continuously moving here and there in all situations. The same environment is kept in all the algorithms position. So all the algorithms are facing the same dynamic situation. Same dynamic situations are created. We have in certain interval, we are just moving these vertical bars from here and there. In this way, the same dynamic environments are created. So this thing, artificial potential field, mostly fail because in dynamic situation, because it stuck in local minima. Now we'll show some simulation hardware experiments video. So hardware experiments is done with the help using this turtle board. This is our turtle board. This is some robot arm with some lidar sensor, 360 lidar sensor, and this is the optic camera which I referred in previous slides for localization. This for hardware. This is the optic motion capture system. So that motion capture system's camera looks like this one. This is the OptiTrack system. So we have 8 OptiTrack camera system in our lab. That OptiTrack camera system tracked this robot's position with some sensor. These sensors are robots. These markers. These are the markers. These markers are continuously tracked by this OptiTrack camera system, and this is helping us to localize the robot. Okay. The environment is size is like that. Now this is the video. So basically, for real experiment, this one initial video you have seen maybe. So this one basically the RQT. This is called RQT graph in ROS. So in which node? Basically, in ROS, what happens while we are using ROS? ROS helps us to communicate from one node to another. Node means you can simply consider. Suppose I am doing planning. So planning means I am sending some command velocity, nothing else. So I'm telling just robot go move in a particular direction with a particular velocity, and simultaneously my other node, maybe OptiTrack system, is sending me robot's current position. So robot don't know from where I have to move until I get some information from the OptiTrack localization system. So that node interconnectivity. Okay, these are basically shown here. That which node and how the communication is happening, information is flowing from where, which location to where. So this is the entire system. Now this is our hardware experiments. Okay, in hardware experiment, one most important thing you can notice is that these are the velocity profile. So velocity profile this is for only for done for DWA and our proposed approach only SLPSR. So bottom one is the our approach, and top one is the state of the art approach you can consider. So here velocities are, you can just notice how velocities are moving. So here velocities are very smooth compared to other velocities. In our case, see here how jerkiness are here. Here velocity is smoother, little bit less fluctuations. Here see how both linear and angular velocities. First one is the linear, second one is the angular. So this is basically real-time screening from ROS to for velocity yeah, acceleration. Now I have some other videos before. Now this is I have shown you these videos for single robots. Okay, these videos, all these things for single robot experiments. Now we have done other experiments also. So whenever this is a different paper, different work altogether, and but there I have shown only one robot is planning. Now in warehouse there will be multiple robots. So many robots will plan together. So what will happen then? Then robots will go from one location to another. They may collide also. So many things will happen. So this is basically something like scheduling algorithm. So this is the one work where I'm not going in details about the theory and all these things, but this is some work where robot can manage their planning uh, in a multi-robot situation. Okay, and it can scale up to 1,000, 10,000 robots altogether. So here, this is our proposed approach. This side. Okay, and this side is basically this is a work with based on game theory. Okay, I'm not going in details about the game theory, but the idea is that this right side based on some Nash equilibrium approach you can consider, and the left one side is basically based on some egalatory correlated equilibrium base where you can maximize the least efficient agents reward. So here you can see that robots are immediately getting some path. Okay, robots are immediately whenever it will start, just and pause there. Here, so you can see here there are no paths. These small dots you can these are the robots. Okay, so robots once they get some task from the server that I receive some task, I have to now go and execute. Okay, this is so will both the robots get tasks. Okay, now they get immediately some paths, but they don't get, they cannot compute because they are not, Nash equilibrium is unable to offer get find out any solution immediately deterministically. But this correlated approach immediately finds some solution and they move, starts moving. But Nash equilibrium based approach gets paths. Sometimes it don't get path also, but if it gets, it will take much larger time compared to this one. And we can scale it up to 1,000, 10,000 robots. So mostly these are developed for warehouse applications. Now that's all. If you have question, then you can please ask me. Hello, am I audible?
Yes, sir.
Okay. Now, if you have any question, then please ask me. Then I'll be happy to answer.
Thank you, Dr. Sadhu, for the wonderful and lucid presentation. And obviously, it's a big, difficult topic, significant topic, and 1.5 hours is not that much sufficient for our audience. So we will be eager to listen from you in near future. So it's now time to take a few questions from the audience. If you have any doubts, you should not hesitate to ask Dr. Sadhu right now. So, any question from your side? Any question from the participants? I think they need much more time to understand your lecture, and we will be sharing the video lecture with them. So, on behalf of this ATP as well as on behalf of the participants, I thank you. I mean, for this enlightening lecture and for the lucid presentation, because this is, as I have said, is really a very difficult topic, and the way you have illustrated is really easy for us to follow. And if there is any further query or doubts from the audience, we will surely communicate this to you at the earliest. So, is there any question from Dr. Chandramurthy? I can't read the name. There is some problem in my screen. So I just see that one. No, I don't think. I think this is by accident. The hand is raised. So again, Dr. Sadhu, thanks a lot. We are really grateful to you as you have managed time from your busy schedule to enlighten us with your knowledge. Thank you. Thank you very much.
Thank
So
you.
yeah,
I just want to say a few words, Dr. Pratusha and Dr. Sadhu, that we can wait for a 2 to 3 minutes. I just want to take from you, so that I would like to request all my participants to just turn on their camera so that I can take the screenshot for attendance of this session. Please, dear participants, just turn on your camera for 2 to 3 minutes, please. Thank you so much, participants. So you may proceed, Dr. Pratusha.
so
Thank you.
start from 7:30 or we can be back by 5 minutes.
Uh, we will need to check whether our next resource person is ready or not. Just give us 5 to 7 minutes so that we can contact him. Because this session is now ended by 7:13, 7:15. So we can take 5 to 7 minutes so that our resource person can be ready.
For confusion, we can start from 7:30 sharp.
Okay, okay, sure, sure.
That will be easy for all of us to follow. I
Yes,
mean, if
yes, yes.
we attend from
It will go for
7:30,
the schedule also, right?
yes, yes, it will go as per schedule because it's a matter of only 15 minutes. So we will start from 7:30. So dear participants, please be back by then. We will start 7:30 sharp. Thank you.